This is section 3.4, direct variation. Bianca is saving her money to buy a designer purse that costs $295. To help raise the money, she charges $12.50 per hour to babysit her neighbor's 2 children. The slope of the line that represents the amount of money Bianca earns is 12.5, and the rate of change is constant. A direct variation is described by an equation of the form y equals kx. The equation y equals kx is a constant rate of change, and k is the constant of variation, also called the constant of proportionality. Example 1. Name the constant of variation for each equation. Then find the slope of the line that passes through the points. Okay, the constant of variation. This equation of this line is y equals negative 4x. And it fits into the equation y equals kx. So the number in front of k stands for your constant of variation. So k is negative 4. And again, k stands for constant of variation. Now, looking at this 2 graph, we have 2 points. We have 0, 0, and we have the point 1, 4. If we were going to find the slope using the slope formula, the slope is 0 minus 4 over 0 minus 1. So the slope is negative 4 over negative 1, which is positive 4. In the second graph, the equation is y equals negative 1/2 x. The constant of variation is 1/2. If we were going to find the slope, we have 2 points, here and here. Now, we could plot the 2 points, label the 2 points 0, 0, and 6, 3. And find the slope using the slope formula. Or we could count it as overrun. Put your pencil on 0, 0, and we're going to go up 1, 2, 3, over 1. Okay, so up 3, over 6. So we can count the rise over run and get 3 over 6. And 3 over 6 reduces down to 1/2. So the slope is 1/2. What can we conclude by looking at our slope and our constant of variation? They are one and the same. So the constant of variation is the same thing as your slope. Example 2a, we're going to graph. We're going to write the slope as a ratio. Again, the slope of the k is negative 6, which is also the same thing as your slope. It's negative 6, and we're going to put it in a fraction, negative 6 over 1. Remember, slope is rise over run. So we are going to plot. You first want to start at the origin. All constant of variation, if it's in the form of y equals kx, that always goes to the line that goes through the origin. So step 1, we want to plot the point 0, 0. That is the origin. Step 2, from the point, from the origin, we're going to move the slope. We're going to go rise over run. And in this case, we are going to go down 6 because it's a negative and run to the right 1. So let's plot 0, 0. Now we're going to go down 6. and to the right 1. I would do it again, except we're going to run out of our graph. So we could put the negative with the 1 instead of the 6. Put up and go up 1 and down and backwards 6. So let's go back to the origin and go up 6, up 6, backwards 1. So we went up and then backwards. And there is your line. I'm off my line. Try that again. Oh, don't forget to label your X and Y axis. Example 2b. We're going to graph y equals negative 3/4 x. Again, this, we need to identify that as a constant of variation graph, which starts at the origin. So we're going to plot 0, 0. Constant of variations always start at the origin, or go through the origin. So that's a good place to start. Plot, label your x and y axis, plot 0, 0. Your slope, which is also, again, also the same thing as your k, is negative 3/4. You can put the negative with the 3, so we would go down 3 and then to the right 4. So from the origin, we're going to go down 3 to the right 4. Do it again. We have room. Or we can choose to go put the 3, positive 3, and put the negative with the bottom. So we would go up 3, and this time we would go backwards 4. So let's go back to the origin and go up 3 and backwards 4. Do it again. If you're given a grid, a quadrant plane, a 10 by 10, put as many points that fit on that graph. The more points you fit, the better accurate line you're going to have. And again, put arrows, and there's the graph. Direct variation graphs. Direct variation equations are in the form of y equals kx, where k is equal to 0. The graph of y equals kx always passes through the origin. Okay, this is a typo right here. K cannot equal to 0. K cannot equal to 0, so it should have a line through it. I apologize that. K can never equal 0. Okay. So in this first graph, this K is positive because it is going upward. In this one, K is negative because K is going downward. It's same thing with M. Slope and M and K are one and the same thing. If the relationship between the values of y and x can be described by a direct variation equation, then we say y varies directly as x. Suppose y varies directly as x, and y is equal to 72 when x is 8. Write a direct variation equation that relates x and y. Okay, right here, the fact that it says y varies directly as x, that means we are going to use the direct variation equation. So anytime you see that sentence, you know right away you're going to use the y equals kx, the direct variation equation. Now let's plug in what they gave us. Y is 72. X is 8, so we need to find k. We're going to divide by 8. So 9 is equal to k. So the direct variation equation, now we're going to plug in what our k is. So the direct variation equation is y equals kx. That is the direct variation equation. Part B says use the direct variation equation to find x when y is 63. So we're going to use this equation, the direct variation equation that we found in example A, to help us find x in example B. So y is 63, so that 63 is equal to 9x. Divide both sides by 9. 63 divided by 9 is 7. So 7 is equal to x. Now, make sure that back up in example A, after you find k, don't forget to write the direct variation equation with x and y staying x and y, and you plugging in k for x. This is the direct variation equation right here. These are kind of like points. Like x is 7, y is 63. That's a point for this line. Example C, 3C. Suppose y varies directly as x and y is 98 when x is 14. Write a direct variation equation that relates x and y. Okay, so right away we're going to use, because it says y varies directly as x, we're going to use this formula. We're going to plug in y is 98 and x is 14 to find our k. Divide both sides by 14. And I do believe 14 goes into 98 7 times. Yes, it does. So 7 is equal to k. We are not done. That's like part 1 of the answer. The next answer, the true direct variation equation, is plugging in 7 for k. Y equals 7x. That is the direct variation equation. Now, that was part A. This is part B, if you want to say. And then part C is finding another set of points. And this time, they give us x, so we have to find y. So we plug it into this equation. So y is equal to 7 times negative 4. So y is equal to negative 28. So that is the answer to the second part. So it's kind of like you have 2 points. The first point was 1498, and the second point will be negative 4, negative 28. And here's the equation of the direct variation. Example 4. The distance a jet travels varies directly as the number of hours it flies. A jet traveled 3,420 miles in 6 hours. A direct variation equation for the distance d flown in t time. Use the distance formula and solve for r. Okay, the distance formula is distance equals rate times time. And it says solve for r. So we're going to divide by t. So r is equal to distance divided by time. Now, let's put in what we know. A jet traveled 3,420 miles in 6 hours. So that is going to be rate is equal to 3,420 divided by 6. And 3,420 divided by 6 is 570. So the rate is 570. And that's 570 miles per hour. So we're going to plug this back into the distance formula, because if you notice, the distance formula is very similar to the constant of variation. So we can use that. So distance is equal to rate times time, and our rate is 570. So what that means is that for every hour, we increase the distance by 570. Now, we need to graph this equation. We know it's going to go through the origin, 0, 0. However, we can't rise over run 570 over 1 is next to impossible doing that on a graph that is not counted by ones. So what we're going to have to do is make a table. And instead of x and y, it's going to be t and d. Now we can make a few numbers for our table. Obviously we have 0, 0. I'm going to skip and I'm going to do, let's do 5. So I'm going to multiply 570 times 5. And I get 2850. So then I'm going to go to 8 for 8 hours. So 8 times 570 is 4,560. Okay, so technically that'll be 3 points. The 0, 0, and then I'm going to plot 5, 2850. So go over 5, up 2,000. If you will notice the y-axis, or in this case it is the d, the distance, and the time, we're counting by thousands. So I am estimating, and 2,850 is about right there. And then 8, 4,560. Oops, thought I added the line. Let me. Okay, example C says, estimate how many hours it will take for an airliner to fly 6,500 miles. Well, here's 6,500 is about right there, so it's going to be on the line. It's going to be past 10. I'm not quite sure. What we could do is plug in right here for D, 6,500. And divide. So 6,500 divided by 570 is equal to about 11.4. So the time is about 11.4 hours. Sorry, about 11.4 hours. A hot air balloon's height varies directly as the balloon ascends time in minutes, 350 feet in 5 minutes. Write a direct variation for the distance ascended in time. Okay, so we're going to use the formula distance equals rate times time. The distance is 350 feet. We don't know the rate, and the time is 5 minutes. So we're going to divide by 5 and get 70. So 70 is equal to rate. Now, that is in minutes, not hours. So we've got the problem, its distance is equal to 70t. That is our formula. We're going to use that to make our table. And again, instead of x and instead of x and y, it's going to be d and t. Okay, obviously we have the 0, 0. Now I'm just going to randomly pick a number. I'm going to pick 20. Oh, I've got this backwards. Sorry. I'm going to say 20. And again, this is minutes. So in 20 minutes, how high does the balloon go to? 20 times 70 is 1,400. And then I'm going to pick 45. And 45 times 70 is 3,150. Now again, this is your T, this is your D, the distance. So 0, 0, then we go to 20, and then up 1,400, about right there. 45, up 3,100. Whoops, probably a little too high. Oops, that's not it either, sorry. Alright, there's the line. I think I'm off just a little bit, but you get the gist of it. Okay, example C, estimate how many minutes it would take to ascend 2,100 feet. So again, to do that, we would plug in 2,100 in for D and solve. And 2,100 divided by 70, you could do that in mental math and get 30. So 30, again, 30 what? 30 minutes. Estimate how many, and we can look at the graph. Where's 30 minutes? 30 minutes is right here. So go up to about 2,100, and yes, that's about right where it is. Estimate how many it would take to ascend 3,500. Let's estimate first. Here's 3,000, so it would be about right here, which I am thinking it's about 50 minutes. So let's plug in 3,500 is equal to 70t, divide, and we would get, excuse me, I said 30, I meant 50. And we would get 50 minutes. That is the end of section 3.4. Your assignment is page 183, even numbers 10 through 44. You can skip 28. Now make sure that when you go to do the problems, when you're trying to find the direct variation, problems 30 through 33, go back and study work the examples again. Or maybe work an odd problem. Actually, I think this starts with number 24. So go back and look at the examples again, because a lot of people mess up on that. Thanks.